In this video, we're going to continue our discussion of numerical differentiation. And in particular, we're going to talk about a comparison between some of the different numerical differentiation formulas that were introduced in the previous sections 10.2 and 10.3. So for the sake of comparison, data points generated by the range of function y is equal to 1 over 1 plus 25x squared in the range of -1 to 1 are used to compare the different formulas obtained in the previous sections. So first, let's talk about the basic formulas. In the following slides, the exact first, second, third, and fourth derivatives of the function are plotted using solid blue lines. The data points of the original function and the numerical approximation of the derivatives are plotted with black dots. The labels FFD, BFD, and CFD denote the forward, backward, and centered finite difference techniques, respectively. The labels FFD1H1, FFD2H1, FFD3H1, and FFD4H1 indicate the forward finite difference, first, second, third, and fourth derivatives, respectively, obtained using the basic formulas whose error terms are order H. That's what the H1 indicates. This is the same for the backward finite difference. The centered finite difference ones are shown using the labels described here, where the basic formulas whose error terms are order H squared are used. That's what the H2 indicates at the end of each of these labels. So this shows the original function up at the top here with data points at a spacing of H is equal to 0.1. Then each row here shows this is the first derivative, second derivative, third derivative, fourth derivative. This one uses the forward finite difference, the backward finite difference, and the centered finite difference. So what you can notice here is that accuracy is lost with higher derivatives. So if we just look at one of the columns, the first derivative, it provides an okay approximation, for example here. The second derivative starts to provide less accurate results, and the accuracy continues to worsen as we move higher up. And so when you get to the fourth derivative here, you can see that outside of these quite flat regions, the accuracy of the derivatives becomes quite poor. It's better for the centered finite difference compared to the other ones, but you can still see even with this spacing H that in this region here that the accuracy is not great using up to the fourth derivative, where the first derivatives it's not too bad. So this is using a smaller spacing, H of 0.01, and you can see much better accuracy here. So we get a better approximation with a smaller H, which is clear since the errors are related to the order of our H, our choice of H. You can see even, so for the centered finite difference in particular, with the fourth derivative, we get a very good approximation of the derivatives all along the function, even at this area of high changing derivative. So let's look at a few things to note. So in general, the centered finite difference scheme provides more accurate results compared to the forward finite difference and backward finite difference schemes, especially for the higher derivatives, for the second and third derivatives. So this shows the second derivatives in the first row here and the third derivatives in the second row with the forward finite difference, backward finite difference, and centered finite difference schemes. And you can see that the centered finite difference has higher accuracy compared to the other schemes. So where the data points here follow quite nicely along the line, and here they're not too bad other than kind of at these points, where these ones start to have some inaccurate results at this area of a quickly changing function, and similar to the backward finite difference. So for all the formulas, accuracy is lost with higher derivatives, especially in the neighborhood of x equals 0 for this function, where the function and its derivatives have large variations within a small region. So this shows the most accurate one, which is the centered finite difference, and you can see as the derivatives get higher, we get less accuracy, and in particular, kind of in this region around x is equal to 0. We also can note that the forward finite difference uses the function information on the right of the point to calculate the derivative. And so the calculated derivative appears to be slightly shifted to the left in comparison with the actual derivative. So it appears to lag. And you can see that here. So the actual derivative follows along here. And if we draw a line connecting the approximation of the derivative, it seems to follow like a similar pattern, but it's just kind of lagging behind the actual derivative. So you can see this kind of shown here. Similarly, the backward finite differences scheme uses the function information on the left of the point to calculate the derivative, and so the calculated derivative appears to be slightly shifted to the right in comparison with the exact derivative. So it appears to lead the actual derivative, which you can see here. The centered finite difference does not exhibit the same behavior because it uses information from both sides. So it's more balanced and it provides a more, it doesn't have this kind of leading or lagging skewness to it. Another thing that we can note is that when we're using a small step size, so h less than 0.01 in this example, the formulas provide a very good approximation with the exact derivatives, almost exactly overlaid with the finite difference calculations. And so this is for all of the schemes, the forward, backward, and centered finite difference. When we use a small step size, they all provide very good approximations of the derivative. Here you can just see this very slight lagging in the forward scheme and very slight leading in the backward scheme, and an excellent approximation using the centered finite difference scheme. For both of this is showing the third derivative as well as the fourth derivative. For a larger step size, so for example, h greater than 0.1 in this example, the approximations for higher derivatives are far from accurate, especially in the neighborhood of x is equal to 0 for the higher derivatives. So even using the most accurate scheme, the centered finite difference, you can still see that the derivatives are not very accurate around, especially around the x is equal to 0. And it's quite poor for the forward and backward finite difference schemes. So for any of the schemes, as we increase the order of the derivative that we're taking, the errors just tend to compound, and so we lose accuracy as we increase the order of the derivative. The other thing that you can notice is that for the forward finite difference, the first derivative at the last point, so x is equal to 1, is unavailable. So you can see at x is equal to 1, we don't have any derivative calculated. And this is because it uses the function values after the point. So if we want to calculate the derivative at xi, we need xi plus 1, which means when we get to the very last point, we can't calculate the derivative there because we don't have another point after it. Similarly, for the backward finite difference, the first derivative at the first point, so x is equal to minus 1, is unavailable. And this is because the scheme uses the points before the one that we're interested in to calculate the derivative. So if we want the derivative at xi, we need to know the function value at xi minus 1. So for that very first point, we don't have any points before that, so we can't calculate the derivative there. The centered finite difference, the first derivative at the first point, so x is equal to minus 1, and the last point, x is equal to 1, are both unavailable. And this is because the centered finite difference uses a point before the one we're interested in as well as a point after the one we're interested in. So we can't calculate the derivative at both the first and last points. And this carries on for the higher derivatives, with the second, third, and fourth derivatives being unavailable for the last 2, 3, and 4 points, respectively, when the forward finite difference scheme is used. So you can see this is the second derivative. It's not available for the last 2 points. The third derivative, it's not available for the last 3 points. And the fourth derivative, it's not available for the last 4 points. The situation is reversed for the backward finite difference. So for looking at the last 2 points, 3 points, and 4 points for the second, third, and fourth derivatives, respectively. And the centered finite difference scheme provides more balanced results. The first and second derivatives at the first and last points are unavailable. So this is showing the second derivative here, and the third and fourth derivatives at the first 2 points and the last 2 points are unavailable, as we can see here. So now let's talk about the higher accuracy formulas. So the observations for the basic formulas carry over to the higher accuracy formulas, except that the results are unavailable at a larger number of points on the edges of the domain. So we can notice that the first derivative is unavailable at the last 2 points because the forward finite difference higher accuracy formulas use the information at xi plus 2 to calculate the derivative at xi. Similarly, the first derivative is unavailable for the first 2 points in the backward finite difference higher accuracy formulas because the scheme uses the information at xi minus 2 to calculate the derivative at xi. For higher derivatives, the more results are unavailable at larger number of points close to the edge of the domain. Similar to the basic formula scheme, the centered finite difference provides more balanced results, with the results being unavailable at the points on both edges of the domain. This is showing a comparison between, for the basic formulas and the higher accuracy formulas, with 2 different choices of our step size h using the forward finite difference scheme. So you can see that the higher accuracy formulas tend to be a bit more accurate than the basic formulas, but the main thing that you can see here is actually that for a larger h, both approximations provide a pretty good approximation for the first derivative and for the flat parts of the higher derivatives. And as explained previously, the derivatives calculated using the formulas appear to be shifted to the left in comparison with the actual derivatives. For a smaller h, both schemes provide relatively accurate predictions. Similar observations can be made for the backward finite difference, and here again the formulas appear to be shifted to the right in comparison to the actual derivatives, which is slightly obvious when we use a high or a small h, and it is quite obvious when we use a larger h. For the, this is showing the centered finite difference here, and you can see when h is less than about 0.2 for this example, all of the derivatives except for the fourth derivative at x is equal to 0, using both the centered finite difference schemes provides predictions that are very close to the exact results. So it's obvious for from these figures that when h is relatively large, a centered finite difference scheme is perhaps the most appropriate, as it is more balanced and provides better accuracy. So you can see here using even a large value of h of 0.1, and looking at the fourth derivative, the higher accuracy, or the centered finite difference provides a pretty decent approximation, especially using the higher accuracy formula. And that is, in comparison to the forward and backward finite difference schemes. For the smaller values of h, all of the schemes provide relatively acceptable predictions, with the centered finite difference having an excellent prediction with an h of 0.01 in this case, using both schemes.